All right, this is the memo for weekly test 9. This one was an interesting exercise because actually there are a lot number of different answers to each of these questions over here, where you have to select a series of reagents that you would choose to do this reaction. Each of them was worth 2 marks. The first thing was, of course, identifying the other starting material that you would need. So in this case, you can see we formed this bond over here, so it must have arisen from the aldehyde that looked like this over there. In the second one over here, we recognize that we connected there, so this has just come from benzaldehyde. And most of you got all these things correct, so that wasn't a problem. I'm just doing it on the side. We'll come back to the actual reaction. Again, we're connecting here, and so it was a phenyl with a aldehyde like that. If you look at that, this is where the connection is. Okay, so those were pretty easy. The hard part is actually saying, well, how are we going to mix these two together in order to get this product, and what conditions are we going to use? So in each of these we have to take note of the various things that we've got in here. So we've got a non-enolizable aldehyde over here, although one can argue that it could be enolized at this position. It's just much more extended conjugated system. But the more important thing over here is that we've got an unsymmetrical ketone. We want this carbon to be the nucleophile. That is the result of a kinetic deprotonation. So one thing that could work in this reaction is to use LDA to deprotonate, form the enolate. So we would add LDA, obviously at minus 78 degrees Celsius. And the second step would be to add our aldehyde, which is that one over there. And that's fine. The last step will be adding some a weak acid as workup, but it's actually not important to write that. It's normally understood that that's what we would do in a reaction, but it's completely not wrong just to write H3O plus as a part of workup. So that would have worked. Obviously, a silyl enol ether would not have worked because it would have gone on this side unless you'd done the silyl enol ether via the kinetic enolate first. So kinetic enolate and then trapped the silyl enol ether, then added it in the presence of a Lewis acid. You could have done that. An enamine would not have been a good idea. It would have been formed on the other side over there to be conjugated with the aromatic ring. And then an azaenolate could also have worked, but those options would really have been rather excessive. They're not wrong, but they would have been excessive. So in this one over here, we want an aldehyde to react with a non-enolizable aldehyde over here. It might be tempting to say, because we can see the E1CB mechanism has taken place over there, it might be tempted to say we're going to mix these two together in the presence of base, but remember this can self-condense, and so we have a problem. We can't actually we can't have this in the presence of a weak base. So now we have to use our specific enolate equivalents. So we can't use LDA because that's not going to work well at all. It will self-condense using LDA. So our options are either a silyl enol ether or an enamine would have worked as well, or an azaenolate. Azaenolate would have also been quite an extreme case, but there's 3 different things that you could have tried there. So the silyl enol ether, the enamine, and the azaenolate would have all been okay. I'll do the silyl one. So TMS chloride plus triethylamine. We normally do that in DCM as a solvent. Second step, once we form that, so with the silyl enol ether, we're going to add benzaldehyde, but remember we need to add something that activates this, gets us to react. We need to add a Lewis acid of some form. So yeah, let me just use titanium tetrachloride. Okay, and at the end of that reaction, again, it's kind of just assumed that there would be some kind of workup with water, so just a mild, just to protonate the alcohol that's formed. You get the TMS alcohol at the end, but that needs to be protonated. Whoops, I've answered this too quickly and forgotten that we actually need to do an E1CB to get this. So actually, this last step over there needs to be treating it with a weak base like sodium hydroxide to get the E1CB elimination to occur. Right, okay, so then the last question, acylation alpha to an ester. Again, this time we've got an enolizable aldehyde. We've got an ester. Esters can self-condense with each other. If you treat this, because of this enolizable aldehyde over here, you can't treat it with a standard base like sodium hydroxide or sodium methoxide, because this will self-condense. So again, we have the same problem that we actually need to go through some sort of specific enol or enolate equivalent. We have two options here again. The one is either a lithium enolate, because we can deprotonate alpha to an ester and it's not going to destroy it, use a bulky base, LDA, and that'll work. And the other option is the silyl enol ether. We make the silyl enol ester, and that also would work as well. We can't form an enamine because the amine is going to substitute the ester, so that's not going to work. We can't do an azy enolate because again the amine is going to substitute the ester. So the two options here are the silyl enol ether and LDA. So I'm just going to use LDA again. But neither is necessarily a better one than the other. You would have to just try this out for yourself to see which one would actually work. Second step is adding this, and this case over here, I'm not going to want to eliminate, so I'm not going to add any base, just the H3 plus there. I'm not going to make that mistake. Okay, and then the last question over here, this one I had a few bizarre answers to. This is a symmetrical diketone. When this deprotonates, obviously it's not going to fully deprotonate. There's a very, very minor amount of enolate gets formed. There's an option of deprotonating there or there, and obviously whether it's there or there is the same thing. If we deprotonate here, well, then this carbon is going to react with that carbonyl carbon over there. So 1, 2, 3, 4, 5, 6-membered ring. If we deprotonate here, then it would have to react with that with 1, 2, 3, 4-membered ring, which is not going to happen. Okay, so it's much better that we take the base and deprotonate there, form the enolate, and there. This then comes back and goes into there. So now we form the 6-membered ring. Just switching things around a little bit over here, connecting to there. So count this: 1, 2, 3, 4, 5, 6, and 7 over there. There's carbon 1, 2, 3, 4, 5, 6. 6 is connecting to 1, and there's 7 over there. A lot of people forgot this methyl group when you worked everything out. Because we're under these conditions, it's under thermodynamics, so this we're not going to form the alcohol, we're going to do a full-on condensation. We are going to end up protonating. Either the water or ethanol that's present can donate a proton, it doesn't really matter, and end up with this. And then we deprotonate and we do this E1CB mechanism. And we get the final product is the cyclohexenone. Don't forget that methyl group that's on there. All right, that was the answer.